Hello and welcome. Here we are in lecture 8. So this lecture is ambitiously titled Arbitration. Really, it's actually kind of a fun lecture. Sorry for the recording and take this off. Um, to get into what we can really do with chisels. So remember in the last lecture we covered decoupling. We talked about using this ready valid signaling and how we could use the decoupled thing inside chisel to make things a little easier to work with. We're going to use that as a building block to build up more sophisticated things today. And for reasons I don't fully understand, when I put this course online, I should do every quarter. This lecture always gets an order of magnitude more views than their lectures, and I don't know why. I hope it's not. That's really confusing. Everyone wants to keep rewatching it. I hope that's not the case, but it'll be a good mystery to figure out someday. So, what are we going to do? Well, we're going to talk about a few different forms of arbitration. You can see that's point number 3. Before we get there, we have a few things we want to cover first. Something called one-hot encoding, which perhaps you're familiar with in Verilog. Um, and we'll talk about how to do that more elegantly in Chisel. Talk about priority encoders, and then finally talk about arbiters and a crossbar. Okay, so let's go ahead and load things up. Great. And okay, so let's start off with one-hot encoding. So it's a design technique in digital design where we say, hey, this is a one-hot encoded bus. So it's a collection of wires where the rule is that exactly one wire is 1. So all of them being 1, no. All of them being 0, no. It has to be exactly one wire being high. And if you can have that invariant held true, it makes a lot of other things in design easier to kind of reason about. And so there's a few different examples this comes up. Some things you might think of, for example, maybe like in the processor design, inside the register file, when it comes time to actually write a register, you only want to write one register, right? You don't want to write multiple registers. So you actually want only one to be high. Or perhaps you're even designing an SRAM. You only want one row to be high. So that's called, a decoder is a thing that does that mapping. In some of the scenarios I just described, it's okay for them all to be 0, but normally one hot means exactly one must be hot. And hot meaning equal to 1. And so the reason why we even mention one-hot encodings is that sometimes, based on the ways your circuit's laid out, and the parallelism is kind of intrinsic to it, you compute something, and the results already kind of are one-hot. And if you can leave it one-hot and then use it someplace else, you can avoid the need to encode and decode, etc. So to kind of get into this world, we are going to use a one-hot encoder right now. But you're going to see some examples in just a few minutes where we're going to keep things one-hot, and they'll make things kind of easy from there. So to kind of summarize what we're doing here, we're taking, in this case, say a number, which is a normal dense number, from 0 to n minus 1. And we're going to go ahead and turn to one-hot encoding. So after it's gone through this box we're building, exactly one of these wires is going to be 1, and the rest are going to be 0. And this number determines which one of these wires becomes correct. So this is all, if this value is here is 0, all of these are going to be 0, but just out 0 is going to be 1. Okay, so let's go ahead and try to wire this up. So how might we do this? Well, this is a good example for us to do some generation. In this case, we're going to use a recursive approach. Could easily do, for with a var. We talked about that last time. But here we go, recursive. So if we have just one thing to encode, well, that's easy. It's the base case. We can just do a comparison. But then building up, what we're going to do is we're going to say, hey, is the thing I'm looking for match me? That's what this is. If that's result of this is going to be 1, great. If not, maybe it's the rest of me. So we're going to kind of concatenate things together. So this is one of those ones where you kind of think about what's going on. We're going to start off with a number coming in, and then we are going to compare against it for every possible value. You can see how index initially is going to be 0. And then as this recursion continues, we're going to keep adding 1 to index. And you can see this base case is when index reaches out with -1. And so in each of these calls, we're kind of constructing it together. So the result's going to be we're concatenating together a bunch of situations where we're seeing does this match up. So maybe some of these ones, maybe it's more clear if we go ahead and run this code. And on the next slide, I have the Verilog. And so the Verilog, you can kind of see this is, a bunch of these comparisons, right? Is it 3? Is it 2? Is it 1? And then we start concatenating things together. Cool. And so if we actually want to go ahead and run this, if we go back a slide, oops, not that one. We can go ahead and print out what we're doing so we can kind of have good visibility on how this comes together. What happens? Okay, so for example, we send in 0. Well, In the one hot encoding, the lowest bit's going to be 1. Okay, we send in a 1. The 1 bit's going to be high. We send in a 2. The 2 bit's going to be high. And we send in a 3. The 3 bit's going to be high. So you can see in this case, because we're representing between 0 and 3, we need 4 bits, right? It's 4 things to kind of represent this one hot encoding. Because of the behavior of printf in this particular language, it's not printing the leading zeros. But you can imagine there'd be zeros there. This is kind of behavior of the one hot things. This is the thing we're trying to build. We built it here recursively. And in this course, I always mention how sometimes we build things that are very common that you should be aware of. The standard library has them. So the standard library also has one of these, right? So this is in the standard library, and so it's going to have the exact same behavior. It's going to implement the Verilog a little differently. I'm curious, can anyone guess a simple way to implement this functionality? Yeah, exactly. Yes, they're going to see that in a second. So, oops, I can turn up the print statement, but yes, they cheated by doing a print statement. Or sorry, not print statement, they left shift. So yeah, here we go. So let's talk about how this works, right? So basically what it's saying is we're going to do a dynamic shift, right? So this input to the shifter is actually input dependent, right? It's not actually known at, hardware generation time. And so a dynamic shifter in hardware is actually not a super cheap component. Even though it's really easy to write in Verilog, in terms of how it actually gets turned into hardware, that could potentially be done in a variety of ways. You could do that with giant mux. You could do that with many small muxes cascaded. You can do it with logic gates. There's a lot of different ways to implement a dynamic shift in hardware. But for now, that's below our level of concern. That's the ASIC CAD tools job. But I'm just showing us an example of, oh, wait, here we have a functionality we want. And if we have a good enough API and a good enough abstraction layer, the internals, are hidden from us, right? It doesn't matter. And so, yeah, so I did it, one way kind of, as an example to gratuitously show off how to do recursion for this. But yeah, you can see how the built-in one did it kind of very nicely with the dynamic shift. Where you say, oh yeah, if this number here is 0, well, this shifts over 0 times, so you get a 1, right? This is, a 2, we shift over 2 times, so we get the right behavior. Cool. Okay, well, let's keep going. So that's how we might build like a one hot encoder. What kind of stuff we can do? Well, let's build up one step deeper and build what's called a priority encoder. So there's a lot of times you have a hardware design problem, you realize, oh wait, like actually in order to build this thing I'm building, I really need a priority encoder. So as you can imagine, there's actually, things built into Chisel Standard Library, so you can just yank one of these, but we're gonna go ahead and build one first to kind of see how it goes together, right? So what's the idea of a priority encoder? The idea is you have some number of requesters, or some number of wires in this case, and you want to pick the one that's highest according to some sort of priority, right? You use some sort of notion of priority, and you want to pick that one, right? So I have some contrived examples here. For example, like in a pipeline processor, when it comes time to forwarding, you want to forward the last write to that register, right? So say if 2 instructions are writing to a certain register, you want the one more recent to get the newest value. That's kind of a very specialized case. More generally, maybe you're trying to find a free slot. So you have a bit indicating something is full or empty, and you want to find the first free slot to kind of fill things in your data structure or something like that. And so there's a number of cases where these priority encoding scenarios emerge. And so you can see there's a few of them kind of here. And so the Chisel Standard Library has a couple of them, right? So it has, priority encoder, one with one hot. So in the Chisel Standard Library, you often see this 0h name and things, and that implies it's one hot. And actually, it's very common when you have a priority encoder that you're going to, take the result of that priority encoder to select between options of a mux. And so to make life easy, they have a priority mux where you can just take directly with the things you want and the thing to select priorities from. It just does both. It does both the priority encoder and the mux one hot for you, kind of all in one module. So kind of a very common, handy thing. Let's go ahead and see some examples of this and actually talk about building our own. So if you talk about how to build your own, there's 2 approaches here, right? And so one, I call it via gates, but really it's just concatenations with a lot of AND gates, right? Or the one to write the muxes. This might be easier to explain, right? So the one the muxes, you can kind of see where, let's say, for example, we say that the lower the index is, the higher the priority it is, right? So index 0 has the highest priority, right? If that's the case, you can see that no matter what's coming in on this input, if this input is 1, this one's going to win out. It's going to say, hey, that bit's the one that's going to be the one that matters. And it's because it's later in the chain, right? So we can kind of override other ones, right? In this one, we're saying this, n minus one is the lowest priority, so that way, it can kind of get overruled, so to speak. Cool. So this is like the mux approach. It's kind of cascaded muxes. Alternatively, we can concatenate wires together. You can kind of see, bit by bit. So, for example, if it's this one, which is the most highest priority, right? Well, if that wire is one, then it's going to win. If that one's not one, and this next one's one, so if the next bit is one and the lowest bit is not one, then this one wins, right? And you can see it kind of has cascades. And so eventually you get this long list of, okay, if this one is one and all the other bits are zero, then do this one, right? And so you can kind of see how this kind of fits together. It's one of these ones where you can toss it at a CAD tool and let it optimize it. It's going to figure out how to, get shared terms across these ANDs. Yes, these ANDs have potentially lots of bits of input, but I mean, it's kind of a price you have to pay for a priority encoder, right? So either you pay lots of, ANDs over here, or you pay it with muxes. The tools can deal with this, but the more general pattern we want, of course, is a priority encoder. In this case, it's a one hot one. So the AND versus coming out is going to be a one hot number that comes out of this thing. Okay, so let's try to write one. And so here's two more examples of us doing these recursive constructions. So for example, with gates, right, our goal was to go bit by bit, and for every bit, it's that bit and all the other bits negated. Let's go ahead and see how that might look, right? It's a little bit complicated. Maybe we'll do that one. We'll do that one first. Okay, so let's kind of talk right through it. So we have recursion. Whenever you have recursion, kind of keeping track of what's your base case. So as long as index is below n minus 1, we do all this. So in other words, our base case is the reverse of this, right? So if index, I guess, presumably equals n minus 1, then we're going to do this other thing, which is just basically we're going to return that index and expression. So naturally, you're kind of wondering, well, what's expression? Let's look at the recursive case. Expression is going to be myself and what was given to me for expression. So you can kind of see, if you go back a slide, there's kind of this growing collection of and terms. This all negated. That's what that's going to be. Expression is actually not going to be negated. It's going to be a growing collection of terms anded together. So myself and everything before me. And then when I actually put this in there, right, then it's like this. Okay, so with gates, we can implement our thing. We'll go ahead and try it out. So we can look at the Verilog and we can see like this, or perhaps we want to run the tiny test case, which I should go turn on printf so you actually can see what it's doing. Yeah, so you can see, for example, okay, we give it 0, we give it a 1. And so now here's a good example, right? Where there's only one bit high, it's easy, right? If there's 2 bits, it's picking the lower one. Or here we also have 2 bits, picking the lower one. 2 bits, picking the lower one. So you can kind of see how this kind of plays out. So this is with our gates implementation. If we go back a slide and look at it with muxes, perhaps to make us more clear, right? We go ahead and do recursively kind of keep muxing things together. We take the current index as a selector. We have that constant, so in the prior slide, we saw it was 1, 2, 4, etc. And so this is a static shift, right? This index is known at elaboration time. And then we also have, put in the chain of the other things recursively. So this one's going to build bottom up. We're going to start from 0 and then build 1, then build 2, build 3. Okay, if we go ahead and run that, same output. If we want to look at the, Verilog, we can do that, and we can see, yeah, here we are with all these muxes kind of selecting between things, kind of cascaded. Cool. Okay, so then naturally you might wonder, well, okay, well, what about the chisel one? Let's go ahead and see how they implemented things. And they use muxes. And so you can kind of see that out. And it's one of these things where if you aren't sure, or you're just curious, you can also go into these API docs And usually you can go get linked to the source. And so let's go see how they chose to wrote it. So they wrote it, as a factory method, right? So here they take in priority encoder, and then, what does it take? Well, it actually takes two different types here. So if you're looking at these kind of confused, it's not just you. Bits is a superclass of both uint and essent. That's what you're wondering. And then this is a sequence of individual bools. So it actually takes either one of those. And then what does it actually do? Interestingly, you can see here, what do? This one gets casted to over here. Over here, we actually just use a priority mux. Pause for a second. Okay, so how does that work? So what we're doing is we're saying, hey, wait, actually maybe it's better if we go back to the priority mux specs. We know what the arguments are. Okay, so priority mux takes in selector and data. Okay, so go back to what we're looking at. We have the selector, which is the input. And then what is the data? This is some sneaky Scala here. This is going to produce a sequence of uints, right? Now, we haven't covered this portion, this is a range. You guys should be familiar with a range. This is the functional programming, that's next week. And then turning into a uint. So yeah, so you can see that at the end of the day, they actually chose to build on top of their priority mux. And so that's why I kind of have these things covered together in our course, is that, yeah, between one hot encoding, priority encoding, there's a lot of kind of overlaps in how these things are constructed and used. Oof, that's quite a bit for all at once. I'm going to pause for any questions on this. Okay, well, we can keep going. Okay, so given the one hot encodings, priority encodings, etc., let's talk about arbitration. So this comes up a lot in systems, especially in hardware, as you have quite simply resource scarcity, right? You have more people requesting things than you are able to provide. And so you have multiple requests, and you only have some availability. So how do you handle this? Well, you need a way to arbitrate, right? And so this comes up a lot of places, right? For example, in the processor, if you have only one port on your memory controller, you need to arbitrate between which core gets access to the memory controller. Or if you have a cache versus the processor who wants a memory controller or something, they all need to kind of differentiate. And so this is a common thing that comes up in hardware, and so we kind of want a way to deal with this. And so in this lecture today, we're going to kind of show it both how it behaves first, and then we'll talk about building your own second. So we're actually, in this case, we're going to start off with the chisel library version, just so we get familiar with how it's going to behave, and then we can talk about how we can go try and build this ourselves, right? And like I mentioned, I've given an example of the processor, but actually, at the very end of today's lecture, we're going to use this to build a network switch, and that's going to be an example we're going to use it for. Okay, so how does this look? Well, the arbiter takes in n requests, and then one of them's going to win. What's interesting is even though I drew these all as one-directional arrows, they actually aren't quite one-way arrows, right? They're decoupled ports, right? So remember, decoupled, there's valid going one way and ready going the other way, right? So on these ports, the valid's going this way, and valid indicates this port is making a request. Port 0 is making a valid request. If the ready goes back the other way, one, that suggests that port 0 was granted the request, right? They won. And so when it comes to arbitration, if there's only one requester, they win. Easy. The reason why you have an arbitration protocol is if there's more than one requester, right? So if there's more than one requester, you need some sort of way to arbitrate, right? And so a simple thing might be, well, what if it was a fixed priority, right? So 0 always outranks 1, always outranks 2, right? That's one possibility. Just there in chisel. You can imagine that suffers from fairness issues. It does. So you could do a round robin, right? That's RR arbiter. They have that. That rotates who wins. And remember, this arbitration, this only comes up if there's multiple requests. Even with these other more sophisticated arbiters, if there's only one requester, that one requester gets the resource. And then there's even something more sophisticated called a locking round robin arbiter, which if somebody needs access for multiple cycles, you don't want them to kind of get their access revoked midway. You can lock it down. Let's go ahead and see this play out. So this is a module we made just to instantiate the chisel arbiter. So in the middle is the standard library chisel arbiter. Great. And so what are we going to do? Well, to kind of make this world look the right way, we're going to have some decoupled ports going in for requests. and we're going to have a decoupled port going out for the result, right? So we go ahead and declare the module, connect up the inputs. So yeah, here we take each of these input ports coming in, connect it up to the arbiter. We can use that full connect feature. It's nice and easy to do most. Remember, there's three things in it, right? There's the ready, there's the valid, and there's the bits. So you can plug in all three together at the same time. Connect up the output too. And then there's some stuff I put in here so we can print the stuff out to make some sense of it in the next slide. Okay, let's go see it. So right now, the internals of the arbiter are kind of a mystery for us. We're just looking at the behavior, right? So let's go ahead and run this little demo. So what are we doing? Well, in this case, you can see not one hop, but in binary, who's requesting. In this case, all four of them are requesting. And this one, the default arbiter has a fixed priority, right? So port 0 is going to win. So that's the one that wins. Okay. Let's say, based on the way the separation is set up, now only 3 of them are requesting it. So port 0 is turned off. Well, now port 1 wins, right? Or then port 2 wins. Or then finally port 3 wins. If they're the only one requesting, they're going to win. And we could do various things, right? Here I have it, greater than or equal to. We can make this equal, and you can see whichever one requests by itself could win. We could, imagine other scenarios, right? What if, for example, we say P is less than 4, which it will always be. Well, guess what? That port always wins, right? Because it's the same request coming in, and we have a fixed priority, and so it's going to keep winning. Now, if we want to fix that fairness issue, we can go ahead and make this perhaps a round robin arbiter. And let's see what happens. And we can see it rotating, right? So it's going to rotate who wins accordingly. Now, in this case, like I said, maybe the work the person needs to do takes more than one cycle. So the fact that they had that grant and now you're revoking it, preempting them, that's kind of problematic, right? So that's what that third one is. That's the locking round robin, right? So go ahead and make this a locking round robin. Let's say now the grant's going to last 2 cycles. Well, then you can see it gets over 2 cycles. So those are the 3 kind of arbiters built in. Yes, question. Sure. Oh, great question. So why in the heck am I calling module right here like that? This comes up sometimes. Yeah, I'll even highlight this so it's clear for the recording. This comes up sometimes with some of these standard library components where we talked about how sometimes we generate chisel that's not a self-standing module. It's just raw chisel put together. And, that's usually okay if that thing ends up being called eventually inside of a module. In the case of some of these components from the Chisel utility library, occasionally you kind of wrap them on a module. You have to forgive me for not remembering the exact Scala, language embedding reason why this is necessary, but I'm pretty sure this is not going to work if I remove this. We'll find out. Oh, maybe. The other one, it seems like it was okay to declare it, but it didn't have it causing exception on the next slide. Yeah, so when it hangs in Jupyter, you kind of got to rerun it and then collaborate. Okay. Yeah, if you take a second peeking at the code, maybe we can discover why this is necessary. So if we go here, oops, you can see even in the example, they show you, they suggest you wrap it. I'm sorry, what's the question? Or yeah, so the question is why, is it always going to be .io? Usually, yes. So like I said, there's actually multiple types of modules in Chisel. In this course, we're basically always going to use module, but there is something called like a raw module or a multi-IO module. A regular module we use in this course has to have a field called IO. Like if you don't have IO, things get a little unhappy. And that's why in this course, we're doing things like putting anonymous bundles inside of our IO, so that way we had multiple ports. You can declare something called a multi-IO module, which can have multiple IO blocks, and they aren't say all called IO because they're different names. Or you're going to have something called a raw module, which doesn't even have necessarily an IO, not required to. But module is kind of the good thing in many cases. In this particular case, I'm not sure why arbiter can't be self-standing, but you can see here it's not self-standing. Yes, yes. So the question is, does arbiter define these IOs? Yes, it does. So, yeah, it has to have a vec probably for these, right? We can probably, heck, let's go peek at it, right? Why not? So we go peek at this. We can see that, okay, here's, oh, that's why. Okay, great. So this is a reverse problem, right? So we talked about this a second ago about, oh, well, sometimes you don't want to make a module, you just want to have chisel. As long as that instantiates eventually inside a module, you're fine. Turns out, once again, forgive me for forgetting my Scala rules, if something's declared a module, to instantiate the module, you actually need to wrap it in a module. Um, yeah, it's a little weird. And so maybe a better way to kind of explain this is actually if I keep going, actually, no, sorry, that's not in the repo. Um, I think the point of confusion is that when we call like test, where's test? We just say new module. What you're not seeing is in the implementation of test, that thing is wrapped inside module. So an instantiated module in Chisel, you need to wrap it in module. Glad we're figuring this all together. It reminded me. Yes, so the reason why that's wrapped in module is because it actually is a module. I know, so that's why you're like, wait a second, wait, so I made the module and have to call it module, wait, then shouldn't I just make things not modules and then look cleaner in my code? Perhaps yes. This is like I said, I'm glad we're having this conversation. I sometimes, you know, don't question things enough because I've written so much. And so I would say this is probably one of my least favorite, I guess, boilerplate kind of warts in the language. It used to be clone type, which we covered out, a couple weeks ago, a couple of lectures ago. They fixed that, so kudos to the dev team. The fact we need to declare module references inside, wrap module references inside module, that's a little annoying. Um, what's actually going on, we can talk about it a little bit. Why they felt the need to do this, I don't know. But so one, when you say extending module, you're extending a class, right? So there's certain things you get from inheritance for that class. The other thing, when we do, if we go back a slide, now we know this actually is calling on the object modules, it's a singleton, and we're calling the applied method. So there's some internal state stuff going on they want to make sure happens when modules invoked, and they want to do it via you calling it on a factory method rather than the class constructor that you're extending. That's the LT why that was chosen that way. I can't explain this. I do remember vaguely like 8 or 9 years ago in like Chisel 1. It may not have been this issue, it was something similar. Scala had a method you could override where this method was guaranteed to run before any child class methods. And we were using that, and we found out new versions of Scala were going to remove that, so they changed the language. That was like 9 years ago. Um, anyways, in this case, yeah. So you have to wrap module instantiations like that. So even if you're not doing testing or not using a standard library, if you write a module, instantiate one of your modules in another module, you do need to wrap it. And yeah, I'll admit that's not pretty boilerplate code. That's annoying. Oh, the one hot encodings. We're going to use that more to build this arbiter. So right now, we taught you about one hot, we taught you about priority encoding, and then you're right, I didn't connect that to arbiters. And we're going to see how we implement the arbiters with those in the next slide. But right now, we'll make sure to understand arbitration. Right? Arbitration, you have multiple requests. If they're all zero, whatever. If exactly one of them is one, they get it. If more than one of them is one, we need some sort of way to arbitrate, some way to choose who wins, right? And so we saw fixed priorities, we saw round robin, and you can imagine this locking round robin. Yeah, so I think in terms of, we're going to apply the one hot in just a second on the next slide. Yeah, let's go ahead and make our own arbiter, right? And so we're going to do this in two passes, right? So I'm going to have one implementation of the module now. Hope this one maybe is somewhat intuitive. I would say somewhat rather, and shouldn't be automatically obvious. And you may see opportunities to make things a little bit more elegant. That's the next slide. Let's go to the first one. Okay, so what does the arbiter have to have? We have a request ports, right? So it's a vector. These are all decoupled. Okay. Um, we have our output. Sure, we can't handle 0 ports. We aren't that elegant. Okay, so what are we going to do? Well, we're going to declare some wires and connect to them, right? So this is one design pattern. You can declare a wire. Remember, when you declare a wire, you need to connect both sides, right? So as a designer writing a module, there's nothing wrong with a wire, but sometimes you can avoid the need for wire. It's actually going to make your module shorter because you only have to connect one side rather than both sides, right? So that's kind of thing. So here we're declaring some wires that are vexed for all the ports. So for example, if we want to get all the valid bits, right? So remember coming in, we have these ports that are a bundle, which is, there's the first is the vec, right? And then you go inside that vec, you get a specific port coming in. And inside each one of those ports, you have, ready, valid, and the bits, right? So if we want just the vec of only the valids, well, we can grab it out like this, right? So we can go ahead and say, hey, we declare the vec first, and then we go through it this for loop, and for every single one, we go ahead and connect it to that corresponding valid inside the port. So this is a for loop that runs in the program when we're elaborating, and it's going to kind of hook this together. And we do the same thing, for example, for bits. We want all the bits. We can get all the bits out. And in terms of who wins, remember the ready from these ports indicates who wins. We're going to say nobody wins at first, and then later on, we're going to go ahead and overwrite that. So first, we can tell everybody, okay, everybody lost. Nobody got it. We want to grab your valids, grab your bits. And then we're going to go ahead and take all those valids and then choose who wins with a priority encoder, right? So we're going to have a fixed product, that original arbiter from the other slide. Okay, so a fixed priority, we can just use a priority encoder to tell us who wins, right? So we have all these bits coming in, boom. And so we're using the priority encoder one hot. So the answer is going to be a one hot number. And then we can do that one hot number for a few things, right? We can use that one hot number to select the output bits, right? So here we can actually feed into a mux that works on a one hot encoded value. Great. This is going to help us get the bits set correctly. We can also see if there's any actual requests, right? So when I first defined one hot earlier in today's lecture, I was saying the one hot rigidly requires it must be exactly one. Chisel takes a more extended view of that, which is if none of the inputs are one, you can have 0 sometimes, right? Which is not normally allowed for one hot encoding. So in that case, if all of these things are 0 coming into this priority encoder, the output's going to be 0, right? So maybe you can revise a definition for this priority encoder is saying this priority encoder one hot. If you give it a non-zero value, it'll give you a one hot encoding. If you give it a 0 value, it'll give you a 0 encoding coming out. Okay, so to know if any of them are 1, what we're going to do is call an OR reduction. This is kind of an unusual thing. So an OR reduction is going to just take all the bits and OR them together. And that's available on uint, but not on vex. So we had to cast this vec bool into a uint, and then we can call the OR reduction. So basically, we're trying to see are any of these 1. And that's what our output's going to say. Hey, did anybody actually make a request? If you have a request, we know the output's going to be valid. If we have nobody making a request, then we know for sure our output's not going to be valid. Okay, so we use this, to kind of determine that. Great, and then what's all this business down here? Well, we need to tell a person that won that they actually won. So how do we go about doing that? We're going to tell that particular port it's a 1. And so in order to know what port that is, we actually have to use an encoder, right? We had the chosen one as a one hot number. And now we're going to have to encode that into a regular number, not one hot, a dense number, in order to set the right value here. And that feels like a little backwards double encoding. We're going to avoid this in the next slide. But conceptually, we're all on page board what's going on here. The other thing we want to cover is that, we don't always set it to 1, right? It's only 1 when the thing is granted. So when is the thing granted? It's granted when it's ready and valid, right? And so we're calling .fire on the output to the arbiter. Remember, the output to the arbiter is attached to something else. Something else is telling to the arbiter. The arbiter is saying, is it valid? And the other thing is telling the arbiter. So actually coming into out here, there is an out.io.out.ready, which is an input to the arbiter, right? And so basically, the request only is granted if whoever's using the arbiter tells it it's ready, right? That's why we're saying we're actually only going to mark that as true. And in this case, like I said, we initially set all the things to false, and then we overwrite one of them here. So it's kind of that last connect semantics we're talking about. So this gets the job done. Someplace a little complicated, a little rough. We'll make it a little more elegant in a second. But questions on this so far? I do want to point out, this is kind of a funny theme. So, earlier in the course, I'm like, oh yeah, we're going to embrace immutability. From a Scala point of view, this is immutable, right? There's no var. All the collections here are immutable collections, all vals. However, we know what's going on. We know that when we make these connect statements, we are very much mutating stuff, right? We're very much taking chisel objects and changing their connections, right? But in terms of the Scala we're writing, the Scala is all immutable, right? We are declaring, a wire of vec. This reference, invalids always point to the same vec, right? The internals of this vec do not change. They are pointers to other chisel objects. Those chisel objects have, internal fields for what they're connected to. That's what we're changing, right? So remember, kind of the mentality of these chisel generators is we instantiate stuff, we connect it together. In this case, all instantiations are done by, immutable Scala, and we're connecting stuff, which is changing the chisel objects down low, but actually not doing so with the Scala. Yes, question. Mm-hmm. Oh, good question. So how does this for loop look in hardware? So this for loop is actually not going to be in hardware. The result of the for loop is going to be in hardware. So remember, this is a program we're going to run in Scala at generation time. So let's say we give it a concrete number of ports. Let's say we give it 4 as the number of ports. Okay, so a concrete number of ports of 4. What's going to happen is this is going to run 4 times. So really what's going to happen when this program runs is that, yeah, we're going to end up with a graph of chisel components that happens to have a vec of size 4. And for each one of those elements in that vec, they're all going to be connected. So that when this function is done, you're going to have a chisel graph that corresponds to the design we want, right? It's going to have, a vec of 4 ports here, a vec of 4 ports there. So these for loops no longer exist, right? Those are just executing to build this graph up, but now the graph exists, they don't exist, and then this graph by the internals of chisels is going to get turned into hardware. So really, like I said, our job is just to instantiate things and connect them. And so the for loop is not going to be in hardware. The for loop is going to be in the Scala program that's generating the hardware. Yeah, so the priority encoder is going to be like actual hardware, right? So this thing here is going to return chisel components that are going to actually be hardware. Or I should say more correctly, calling this thing, this is kind of calling the apply method on the priority encoder one hot object, is going to build up chisel things, and it's going to return chisel things. We're going to have a Scala reference to it called chosen one hot. And with that reference, we can do some of these other things. For example, we can say, hey, here's a reference to chisel things to pass into this other Java Scala thing, or here's another thing. And so, like I said, another way to think of this code is like we're actually kind of like building up a graph, and we have these pointers to the graph. So we're kind of building the graph, and the things in the graph are connecting to each other, right? And so these connect statements, these are us telling things in the graph, we're connecting them together in a certain way. Yeah, exactly right. So to repeat the question, yeah, it's hard to tell between what is Scala versus what is chisel. Yeah, that's a great point. Because yeah, sometimes it varies, right? And I think, like I said, the way to think of it is that at the end of the day, when it comes down to hardware, hardware is instantiations of things like, accessing these bits or, this priority encoder or connections. Everything else is us doing Scala, things, right? So here we are doing a for loop to kind of repeat this. So you can imagine, let's say you didn't have for loops. How would you have a variable number of ports, right? Be kind of, oh shoot, how would I connect those together? And the answer is you are going to need either recursion, a for loop, or later on we'll learn about functional programming. You need something to kind of have that, do something n times. How do you kind of do something n times? Well, you need some sort of way of doing that. Cool. Good question. Yeah. So this is perhaps maybe more complicated if you were doing this as a generator rather than just a single instance. Yeah. So yeah, exactly right. So for in order to how to write one of these on your own, um, I'm perhaps not doing the best job of modeling good technique. My advice is to, when writing these, to make it not a generator first time. Just get an instance running, and then use this agile incremental approach. Kind of keep extending it, right? So so close the loop however you can, right? Just get the simple instance, reduce functionality, no parameters, great. And then okay, we'll make this a parameter. 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 You kind of start making more and more parameterized and more flexible and handling more and more cases. So maybe you might say in the beginning, oh, I can't handle that case. And then later on, oh, what would it take? Then you can handle that case, right? So it's kind of building that up. Cool, cool, yeah. And so example, like here, for example, we don't know how to handle if there's 0 ports. Semantically, I'm not sure what it means to have a 0-point arbiter, but these are the kind of things you could imagine trying to handle later on. Okay, so this is our first version. And we saw, some things we didn't like about it, right? We didn't like that, we have to kind of, when you declare things in wire, you got to connect both sides. This business here where we have things in one hot and then we got to kind of connect it back. That's kind of messy. Last hit semantics can be clean, but in this case, we kind of are deliberately writing something twice. What can we do about all that? Well, let's see that. Here we still use a wire and a vec, but all of a sudden, 2 for loops is now down to 1 for loop and only 1 encoder. So what do? It's actually very conceptually similar. It's just a little bit more graceful use of the hardware here. So we actually still find it convenient for things we do later on to have all of our valids in a vec and all of our bits in the vec. So we still do that. And we go through, this for loop for every port and we connect them all to there. So now we still end up with a vec of valids and a vec of bits. That's still useful functionality. The difference is now when it comes to actually making this arbiter, we can just kind of tie them pretty closely, right? So actually we're going to go ahead and declare our priority encoder earlier. And so remember, because we're using a 1 hot in priority encoder, the output's also 1 hot. And so what's cool about that, as you can see right here, for now assigning the return path for who gets the grant, we can use and see who was chosen, right? So we can select the bit we were on and say, hey, that's the bit that was, and you can see if this is all 0, then it's not chosen. But if it is the bit that was chosen, it's a 1, that's going to be a 1. And then we're going to AND it with the result of, is the output actually firing? Is it actually a grant scenario, right? So all that business kind of folded in together. In terms of the other stuff, right? Yeah, we can take these 1 hot chosens to drive that mux 1 hot like before. And we can still drive the, out valid with the OR reduction. But this is, a cleaner design. And as we were just talking about, right? You can't always write this on your first try, right? It's okay to kind of get something working and look at it and go, oh, this is kind of gross. How do I fix this? And kind of keep revising, improving it. Maybe show it to a friend and get some feedback. Question? Oh, yeah, great question. So in line 11, am I connecting ready to valid? Am I making a combinational loop? Uh, Not quite, but it's now potential, right? So what happens? You're right. This is io.rec versus io.out. These are 2 different sets of ports. But you're right. Now there is a path that goes from io.out to io.rec. So it actually now is a path through there. The question is, does our prior design do that? I suspect it does, right? It's a little bit more indirect. So this other one, you can see, initially we assign io.rec ready to false, but then we conditionally overwrite it based on the results of the other one. So it's not as obvious from the code, but this other one has the exact same pathology. So yeah, so there is a path from the ready on the output coming back through the arbiter, coming out the ready on the front side of the arbiter. That path exists. Which that path is the only thing that's there, you're fine, right? But you're right. If that can think of something else and you get a loop out of the deal, then you have a combinational loop. It's a good question to bring that up. Was there another question? Okay. So yeah, this one's a little bit cleaner. We can go ahead and run and make sure I didn't break anything. Cool. Let's keep going. How are we doing in time? We're doing good. Okay. So we can go ahead and test our own arbiter. This is like a test case like before, but if we actually go ahead and run it, we can see, for example, the scenario we just described earlier. Okay, there's multiple. If we're being clever about who wins, we can do this, right? But maybe we aren't always that clever. Maybe it's only some of them. Well, static priorities, right? So the same winner's going to keep winning. This is why you want a round robin one. But sometimes static's fine, right? Maybe you have a processor and you want the processor to have priority when it's having a cache miss to get that result back really, really fast for a load. You want to be able to outrank the prefetcher or something. Cool. And so, yeah, I mean, so in this lecture today, we've seen arbitration. We've been applying decoupling from the last lecture. We're also getting more comfortable with just having generated parameterizability in these generators, right? We have for loops in this case. In the beginning of the lecture, we had some recursion. We're starting to build more sophisticated things. Cool. Well, let's go ahead and build something in surprisingly few lines that would take quite a few lines in Verilog. So let's talk about a crossbar. So a crossbar is a kind of network, right? You have some number of inputs, some number of outputs, and the crossbar, connects them all, right? So, this input can reach any output, and so, or vice versa. And so this way it's one directional. For now, we're just going from inputs to outputs. Let's say you want everybody to be bidirectional. We just got to kind of fold this around, make these ports match up. But for now, we're actually going to have, even on day one, a parameterizable number of inputs and a parameterizable number of outputs. And you can see, well, how this works. Well, if there's, multiple people trying to write to the same output port, we need to arbitrate that, right? We can only have one packet come through. We can't have multiple packets. So thus, what we're going to have, really, for the most part, is just a bunch of arbiters, right? Each of these output ports has an arbiter, kind of picking who's going to be the input that gets sent through there, and that's what we're going to wire up. Okay, let's go ahead and try that. So what we're going to do is we're going to kind of build up a variety of classes to help us kind of accomplish this mission, right? So as a starting point, let's go ahead and make a message. So our message is going to be a bundle, which has both an address and a payload. Cool. Okay, and then for our crossbar, we can go ahead and declare the IO now, right? So we can see the IO, right? We have num ins coming in on one side, num outs coming out the other end. Okay, so we want to have a vec of num ins on one way, num outs going the other way. And what do we have? Well, we're going to have decoupled messages as kind of the thing we're sending on this port. Because the input we want to be flipped, to make it more clear looking at the output one, you can see, yeah, each of these messages is going to be decoupled. Now, one thing some of the students ask me is, okay, does decoupled go on the inside the vec or the outside the vec? Right? I go to decoupled vec, right? And the answer is, it depends what you're trying to do, right? The coupled just takes what you give it and then wraps that as bits and then gives you ready valid in addition to that. If the entire vec all at once is something that can be ready or valid, then you put the couple on the outside. If what you want is a ready valid per element at vec, then you put the coupled on the inside. Because you're basically saying, hey, I want a vec of things that are each themselves ready valid decoupled. Cool. Everybody on board so far? Okay, cool. Let's go ahead and build this thing up. So remember from the last slide, our goal was to basically instantiate one arbiter per output port and then connect all the inputs to each arbiter, right? So you can see how this is going to be a lot of connections, right? Basically, for every output port, we need an arbiter, and for every arbiter, we need a connection to every input port. Or looking at it from another way, we can say for every input, we need to connect it to every single corresponding input on each arbiter, right? So there's some sort of n squared kind of like connections need to happen here. Okay, let's go ahead and do that. So yeah, you can see here we have these nested for loops. So you can tell, yes, that n squared I just mentioned a second ago. What do we have? Well, so at the top level, yeah, we have a generator for this crossbar, right? Some number of inputs, some number of outputs, and a payload size. We can give that information to our crossbar IO we just defined, and yeah, we've got crossbar IO, great. Let's go ahead and define the arbiters for the outputs, right? So this is one of these cases where we know we want n things. We don't necessarily address them dynamically in the hardware. This is why we're using a seek rather than a vec here, right? So we're going to want num outs arbiters Because the arbiter is a module itself, we need to wrap it in the module declaration syntax. I keep forgetting that. I'm glad we reminded us a few minutes ago. And then we go ahead and what's inside the arbiter? Well, interestingly, we can give it a few things, right? So we're going to give it the messages, the payload, and the number of inputs, the type, right? So it's going to kind of be filling those all in. So yeah, we're going to get this many arbiters. Okay. Then if we keep going down this list, let's go through all the imports, right? So for every single import, we're going to need to grab all the readies for all of the arbiters. Now this name perhaps is not well named. So it says in readies. It's not referring to the inputs to the crossbar. It's referring to the inputs to all the arbiters, right? So you see this for loop is going through every single one of these arbiters into its IOs and then grabbing that ready. Okay, so for every single input port, we're finding all of its corresponding input ports on the arbiters. And then we are ORing them together for an OR reduction to then present back to that input port. Is it ready? Now remember, ready in this case it means ready, but perhaps more correctly, it means you received the grant, you won, right? You actually need to send a message. So remember, we're gonna send a message, .fire when both ready and valid are true. Right now, the ready path is actually kind of like the return path, right? You're thinking more about what's the valid path, which is the next set of blocks, right? And so you can see now for every single output, what are we gonna go? So for every one of these output arbiters, we're gonna go through, and for every output, we gotta consider every input since that's an n-squared combination. First of all, we're gonna kind of pass through those bits, sure. We're also going to take that input's valid, connect it to the valid of the, for every one of these arbiter inputs, we're going to connect it to that external port valid, io.in, so it's the external IO. And is this message destined for here, right? Because every input port can be sending a message, but we'll be going for another port, right? So in this case, we're assuming that address is going to be what port you're trying to send it to. So if I'm port 1, this is addressed to port 2, well, it's not for me. So I don't need to actually assert that valid signal. But yeah, hey, if it's for port 1 and I am port 1, yeah, I do want to assert this valid signal if they're actually making this request with valid. Okay, so we connect up all the bits, all the valid. And then we need to take the arbiter output and connect it to the actual IO output. And wow, we did it. So as scary as this code was, and what is this, 17 lines plus the prior slide of about approximately 15 lines, not even, approximately 25 lines of chisel, we just wrote a parameterized crossbar, which is kind of mind-blowing if you ever actually try to write one of these. Number one, if you try to write one of these in Verilog, you're going to run the problem right away out of the gates, which is it's hard to parameterize, right? Having a parameterized number of ports in Verilog is hard, and having that kind of stuff. You can do it with parameters, you can have some gen vars and some for loops, but it's going to be kind of gross. But also all these connections, right? So all sorts of connections, all sorts of reductions, done pretty gracefully here. In this case, we use for loops. In a week or two, when we get functional programming, we're show how it makes it even more compact with functional programming. We're also getting some reuse here. We took advantage of this arbiter to do a lot of heavy lifting for us. The arbiter is handling who wins the arbitration. It's also doing the muxing internally about collecting the actual right thing. So it's actually doing quite a bit of work for us. Cool. Questions? Okay. Well, so that's our implementation. Let's try running it. Fingers crossed. This is a lot of code. Let's see. And okay, it did something. It didn't blow up. Let's look at what it did. Okay, so we connect up a bunch of stuff. So first off, we say every port's trying to send. And just for clarity, the payload it's sending is its own address. And it's trying to message itself module number of outs. So notice how in this example we have 4 inputs and 2 outputs. In other words, 0 and 2 are messaging port 0, and 1 and 3 messaging port 1. Great. And then going through the output ports, we can go ahead and say, hey, they are all ready to receive. Great. And then we're going to run for 4 cycles, right? And so you can see running over 4 cycles that actually it turns out that initially 2 succeeding the messaging, then 0 succeeds the messaging, then 2 succeeds. That's that round robin arbiter at work, right? So if I go back and say, hey, let's maybe not be round robin, we're going to have a constant winner. It's always 0 and always 1. But yeah, that round robin arbiter is a 2-character change, right? And in this case, they really are equal. So having that round robin behavior is perhaps nice. Might complicate testing later on, depending how you have your testing bed set up. But hey, that's kind of cool. And we can, do various things, right? Maybe we can say, hey, what if they all try to, instead of messaging num routes, what they all just try to message 0, right? Well, you can see everybody's trying to message 0, and only some of them are going to win, right? Okay, cool. Questions? Okay, well, that's the end of today's content. Keep an eye out for future assignments. Right now, the main one is homework 2, due Sunday. And yeah, please keep using Slack to get feedback from both myself and the TA. We're trying our best to keep up in there. And so some good questions, and I'll push tonight some small tweaks for me to clarify some questions already asked on Slack. Great, okay. Have a good weekend, folks.